We hope you're doing well in the last quarter of term. Today it is our pleasure to invite Professor Ian Fleming for a Week 7 talk. Professor Fleming is an Emeritus Professor here in our very own Department of Chemistry at Cambridge, and an Emeritus Fellow at Pembroke College. He has authored many well-known textbooks which have greatly shaped our understanding and learning of organic chemistry, such as Spectroscopic Methods in Organic Chemistry with Dudley Williams, and Frontier Orbitals and Organic Chemical Reactions, which I'm sure you can find in most libraries here in Cambridge.
So, Prof Fleming is, however, best known for pioneering the applications of organosilicon compounds in organic synthesis. This talk will illustrate stories from a career covering a wide range of synthetic organic chemistry, identifying in particular those events that led him to enter the field of organosilicon chemistry applied to organic synthesis, to develop the silyl-to-hydroxy conversion, and to find powerful methods of open-chain stereocontrol. His research into the chemistry of organosilicons is just one of the many innovative contributions he has made towards revolutionizing organic synthesis by creation of new synthetic shortcuts. So without further ado, let's put our hands together to welcome Professor Ian Fleming.
I'll explain the shortcuts later. What I want to do straight away is start at the end. You mentioned it, the silyl-to-hydroxy conversion. Arguably, this is the biggest single contribution I made. And it's sometimes called the Fleming reaction, because I was not quite alone in working out this reaction. All right, well, what is this reaction? Tamau was working in a particular bit of silicon chemistry when he was the lieutenant of Kumada, who was a major organic chemist in Japan. And this was the reaction they were looking at. This is Tamau, and there he is again there with me, sitting at a dinner in Japan, in Kyoto, and you could see I look excruciatingly uncomfortable, and I was. It was one of those Japanese tables that's on the floor, and there was no hole for your legs, and so there you were sitting, and I was, oh gosh, by this stage in the dinner I was extremely uncomfortable. But I managed to get through the time. And we talked about various things there, but this is the background. Tamau was looking at this reaction, weird reaction. These pentafluorosilicon dianides, weird compounds. They're actually beautiful crystalline water-soluble compounds. And with Kumada, he discovered that if you oxidize them with almost anything, they will go from silicon to oxygen. So essentially the silicon is a metal. If you take a metal carbon bond and oxidize it with almost anything, you'll get an alcohol, as long as it doesn't go on from there and go into detail. So the oxidation of silyl-to-hydroxy was something there. But you can see that this isn't going to be greatly important in organic synthesis because we don't usually have pentafluorosilicon dianides displayed. So Tamau then was starting an independent career. And in his independent career, he took away these fluorines one by one until he got to the stage where there was only one left on the silicon. If you took that away, it didn't work. But while you had one on, this reaction takes place. And now we can see what's going on. The peroxide, he found that this was quite good for the oxidation, attacks the silicon and displaces the X group. And once you have an oxygen-silicon bond there, with this weak oxygen-oxygen bond behind it, that oxygen can depart as a hydroxide ion, and this group here on the silicon will migrate to that oxygen. So you replace the carbon-silicon bond with a carbon-oxygen bond. And then when you work up with water, you get an alcohol. So there we are, the silyl-to-hydroxy conversion in Tamau's version. Now, our version, working on it at about the same time, and quite independently of him, of course, was this. We started with phenyl dimethyl silyl groups in all sorts of organic structures. Our had to begin with a different step. We either treated it with acid or bromine, and then we get an aromatic electrophilic substitution that replaces the silicon carbon bond there on the benzene ring with the electrophile, and then the silicon picks up the counter ion, whatever it is, X here or the bromide ion there. And then we're in the same position that Tamal was in. We've got this same thing. And we can do this reaction in a peracid. When we first did it, we used perbenzoic, but we can do it in peracetic acid. And what we get then is the peracid displaces that X group, gives us a bond like this with the silicon-oxygen bond instead of the X, and we've got this weak oxygen-oxygen bond. The benzoate in this case departs, and we replace the silicon-carbon bond with a carbon-oxygen bond. And then when we work up, we get an alcohol. And it's all in one pot. So we start with the phenylamine group, which is a wonderful group because it's got the only reactions it will do is this reaction here, aromatic electrophilic substitution. Otherwise, it's completely inert to almost everything you try to do in organic synthesis. And of course, the polarity of that bond changes from silicon towards carbon. Carbon is more electronegative than silicon. Changes the other way around, now oxygen is more electronegative than carbon. And the size changes. The silane group is huge, with these big bonds stuck to it. The oxygen is quite small. So the change is very dramatic, and it's very easy to do with this reaction. So that's where we're going, because the question is, how was it that I came to make that discovery, if you can call it a discovery? Tamal was working from Kumara's start. I started from something which I'm going to show you how we got to the need to do that. All right, now, why do I call it Shortcuts? Shortcuts is a movie. It's a wonderful movie from 1993, quite a long time ago now, but it's still a wonderful movie to watch. It takes 3 hours and 7 minutes. It has a fantastic cast, wonderful group of actors. And what it does is tell a lot of short stories which interlock. And that's what I'm going to be doing. So it's shortcuts in that sense. They're cuts from stories, and then they're all short, joined together. And that's why I like to refer to it as shortcuts. Also, I don't mind advertising this movie. It's well worth watching. Now, my story, of course, began in 1959. It was directed not by Robert Altman, but by John Harley Mason, who was my PhD supervisor. And later on, of course, I will get on to my own independent career. And with luck, I'll get this talk into 55 minutes instead of 3 hours, whatever it was in Altman's film. All right, now when I started work, it was a long time ago, you can tell. And people often ask me, what was it like to do chemistry without NMR? And we didn't. When I started as an undergraduate here, there was no NMR in the country at all. There were no NMR machines in the country at all. We did have the first one in this country, in this department, a 40 megahertz machine, and it came just about the time I started my research in 1959. And we had the first one in the country here. So most of my research didn't use NMR, but you're going to see something later. And the other question people ask me is, how did we control stereochemistry? Well, okay, how did we manage without NMR? We did, we managed. How did we control stereochemistry? We didn't. And that was the essential story as we began research, as I began research. So let's go back to 1959. Here I am in 1959. And at the bottom right there, you can see a structure of a molecule, which John, my supervisor, had been working on. He'd helped to work out the chemical structure of that one. And they did use this structure down here. So John said to me, why don't we try to synthesize that? So I thought, that's fine. And he gave me a possible approach to that synthesis. What he said was, let's take N-methyltryptamine. That's this molecule here, a known molecule, and oxidize it. In other words, we'll take a proton off and take an electron out of that molecule. We'll have a radical like this. And that's where the most of the radical character is placed. And so the chances are it would dimerize like this at that point. And then, well, to begin with, that nitrogen might well capture here, but if you look at it, you can break these two bonds here and rearrange it around, and it comes out with that structure there. So it ought to go in one pot in one step, or more or less, maybe 2 steps at the moment. So nice, simple synthesis. Right? So there we are, November 1959. I'm told to make that molecule and oxidize it. So I did. I didn't make it by the known route. The known route was long and cumbersome and not at all nice. that this was a modern method in those days, and still is a good method of making amines. You take an amide and you reduce it with lithium aluminium hydride. And in those days, lithium aluminium hydride was not commonly used, but it was available, and I got hold of some and did this reaction. Right, so we convert the formyl group into a methyl group, and it was there, and it had the right melting point for the literature value, so I was pretty sure I got the right thing. But I only did that on a few milligrams. So I then repeated it with a few grams. And I got an oil instead of crystals, and nothing I could do would make that crystallize. So there was some serious doubt as to whether I made the compound this time. I tried scratching it, I tried all sorts of things, tried column chromatography and all, and couldn't get it clean at all. So John, coming around the lab all the time, it was easy enough for me to stop him and say, look, what do I do? I mean, I'm only a very beginning graduate student, and I don't really know what to do. So John said, oh, you talk like that. Oh, take an NMR spectrum. So I said, take an NMR spectrum? What will that tell me? I had heard nothing about NMR. All I'd heard in the lectures we'd had at that stage was the physics of NMR. Nothing about the possibility that it might be useful in chemistry. So I said, right. I mean, obviously, got an NMR. So I took it down to the NMR machine in the corridor around here and got an NMR spectrum back. And this is what it looked like. It was a tiny little piece of paper. I've still got it in my office. This is there. This is in the same photograph to show you how big it was. A little strip of paper came out of the machine with this wiggly line on it. It's got no scale because we didn't have a scale in those days, but it had one thing. It had a little note attached to it saying ethyl group. And I've written it up there, ethyl group. Somebody had written on it, ethyl group. And of course, now, knowing about NMR, we can see why. There's a triplet at the most upfield end of the spectrum. A triplet like that means there's a CH2 group next to it, and that'll be a methyl group, so there must be an ethyl group in the bottom. Ah, it actually did give me the answer. What I got was N-ethyl, N-methyl tryptamine. Now the question is, how did that happen? Well, of course, I know what I was doing with this. So, by the way, I might get slightly better lighting if I did. Was that the answer? No, it wasn't. It's okay. So, what's happening in here? And of course, what I haven't told you is everything that's going on. When I did this reaction, I quenched it with water because I was only doing it on a tiny scale. And although when you quench lithium aluminium hydride with water, you get a lot of hydrogen, there wasn't much lithium aluminium hydride, there wasn't much hydrogen, and I didn't bother about that risk. But when I'm doing it with several grams, I was seriously worried about the hydrogen that would come off, and so I quenched with ethyl acetate. And that, of course, was the cause of the problem. Because what happens is, at the end of the lithium aluminium hydride reduction, we have a lithium salt of the amine. The ethyl acetate acetylates that and gives us a new amide, which is instantly reduced by the lithium aluminium hydride back to an ethyl group, just as the formyl group is reduced to a methyl. And so that's what had happened, and of course I realized what had gone. So, cleared it up. Very nice. Interesting reaction. In fact, what I then did was several weeks of work to show everybody what a wonderful way of making tertiary amines this was. You acetylate, you acylate, make an amide, reduce the lithium aluminium hydride, add the ester of your choice, and you'll get a tertiary amine out. And indeed, I did several reactions like that, and then somebody went and published that very idea, and so I had to stop that. Nevertheless, I now can repeat this reaction and do it properly, reduce the lithium aluminium hydride, but quench with water carefully. And then I got a nice 85% yield of the right compound with the right melting point again, and we're off. And then, sadly, I did lots and lots of oxidations. How many have I said there? 38 different ones. I oxidized it and looked to see what I got, and I could not detect chalicanthine, my target molecule, in the product there at all. And so it was rather a failure. But it wasn't a bad idea, because 7 years later, Ian Scott with Frank McCapra in Sussex showed that this works. And his particular oxidation was first to make the anion with beta grignard take off these protons. and then oxidized with ferric chloride. I tried ferric chloride, but I hadn't used Reno. And it worked. And the first form product was this one, chimonanthe, where that amine attacks that carbon. But that can undo itself and rearrange. And if you boil it up in acetic acid, it goes over to there. Now, stereochemistry. There are only two possible isomers of this molecule, because the constraints of these ring systems is such that you can only form it in two ways. So that center there must have the configuration of that nitrogen on the top surface the same as this bond. And so you can't have the molecule with the nitrogen at the back. It has to be in the front. And so that limits the number of possibilities. Although you've got 4 stereogenic centers, there are only 2 diastereoisomers. And what Frank McCapra got was 19% of the correct one and 7% of the isomer. He also didn't expect to control the stereochemistry, just as I hadn't. And nevertheless, you can separate them and you get the final target point, and in a very simple sense. So that shows you what was possible in those days and how we handled stereochemistry. We made the mixture separate. Anyway, complete useless chemistry. So my supervisor, John, came to me then and said, I think we should stop this, it's not getting anywhere. Here's an idea. How does nature make acetylenes? Now, acetylenes in those days, if you wanted to make an acetylene, what you did was you took an alkene, you added bromine, so you just added bromine, that instantly adds bromine to it, and then you treated it with boiling alcoholic potash. That was the standard recipe. And then you get 2 HBRs out, and you get an acetylene. That was the standard recipe. But boiling alcoholic potash didn't sound very likely to be what plants would use to make acetylene. So the question then was, plants have found a milder way of doing it, so what have they done? All right, well now, one of the ideas that came to John was based on the method by which long alkyl chains are synthesized in nature. This is the standard route. What you do is you start with malonyl coenzyme A here, and you acylate it there. So that acyl group becomes this acetyl group, and the carbon dioxide has come out in order to form the new bond. And then, actually, the ketones reduced, dehydrated, and reduced again. And then you can repeat. You could add another one, and go round and round and round, extending the alkyl chain. And that's in outline how nature does it. So what John said was, what about the possibility that it doesn't lose the carbon dioxide? And we get to a molecule like this. And then, if we made the enol pyrophosphate of that, nature's leaving group is a pyrophosphate, we might be able to get a decarboxylated elimination. And that might be easier and faster than boiling alcoholic potash trying to take a proton off the molecule. And so was this a good idea? Now John gave it to me as his idea. And it's rather interesting that sort of thing can happen. I later discovered it wasn't his idea at all. He'd heard it in a lecture. The lecture had been given by none other than Tim Jones, who was the Waynfleet professor in Oxford. Big name and a big, the senior chair practically in the country. And Jones had suggested it in a lecture. Fortunately, I discovered this and prevented us from claiming this idea as ours. But, okay, Tim had the idea, decarboxylated elimination, but he didn't do anything about it. John came to me and said, why don't we try and see if it's a good idea? So what we'll do is we'll try a reaction like this. We'll make a compound with carboxylate ions here, and we'll make an enol sulfonate as our leaving group there. And then the question is, with this group and that group, does it do the elimination? And that would be a good model for what might be the biosynthetic route. Incidentally, I used the word leaving group. Now, we've got to be careful here. Okay, this loop is the kind of group we call a leaving group. This one is also a leaving group. But then so is the carbon dioxide. And so would the hydrogen be if it were a dehydration type of reaction. So we need a name for that kind of leaving group, this one here. And in just about that time, 1960, a man called Jean Mathieu published that two names would be useful. He said we should call this kind of leaving group a nucleofugal group, because when you take it out with its electrons, it's kind of capable of being a nucleophile. Whereas this kind of group should be called an electrofugal group, because if you take it out, it would be an electrophile. So there we are. We've now got a language for distinguishing between these leaving groups. That was about 1960. But I don't think almost anybody at that time noticed this or paid very much attention to it. And it didn't play a big part in anybody's teaching or chemistry until much more recently. And we do need these words to clarify what we mean by a leaving group. I'll come back to that point later. All right, so that's what we're going to do. So this is what I did. This was a known compound, benzoyl malonate. I took that and I treated it with base and tocine chloride, so I made the enol sulfonate. Or at least I hoped I did. And I got an oil. Another oil. And nothing I did would make it crystallize. Now, most practical organic chemists at that time would have recognized that with a benzene ring and a tocine ring and some polar groups, this ought to crystallize. This should not be a liquid. So I was very doubtful whether I'd really got this molecule, and I certainly didn't know how pure it was. I scratched. It was soluble in benzene, but not in petrol, so I dissolved it in benzene and slowly added petrol till it oiled out, and it just oiled out. It didn't come out as crystals. Nothing I wouldn't crystallize. So what I actually did was to change the tocine group to something that crystallizes more easily. And that's the parabromobenzene sulfonar here. So I made this one, and it was an oil, and it wouldn't crystallize. And I thought, this is weird, because parabromobenzene sulfonate almost always crystallizes beautifully. Now, distraction. Here's the room I did this work in. It's up in the wing of this lab over on the far side. About as far away from here as you can get. Okay, and this tells quite a tale of what chemistry was like. Here, on the right, is the edge of the fume cupboard. We did almost no chemistry in fume cupboards. It had to be making an acid chloride with cyanide chloride before we put it in the fume cupboard. That belches off HCl and sulfur dioxide. And so you don't want to do that in the open chain, open lab. So there was the fume cupboard. I didn't use that. All the chemistry I'm describing took place on this bench. Now, what else? That there, that slab of white, that's asbestos. Which is on the bench as insulation, so that when I put down hot vessels, it didn't upset the teak of the lovely wood bench. Over here, that's another slab of asbestos covering a pudding bowl containing concentrated sulfuric acid and potassium dichromate in soda. And that's how we cleaned our flasks. When you finish your reaction, you washed it out with water, and you put it into the pudding bowl overnight, took it out in the morning wearing rubber gloves, good rubber gloves, washed it in water, and it came out beautiful, glistening, clean. And that's what we did. Down here is where I'm storing my solvents. This one here is ether containing sodium wire out in the open on the shelf there. So you can see things were pretty different. Well, there I was. I had a flask like one of these round bottom flasks containing this oil. And I was all set to give up. So I took one of these wash bottles, which I thought contained acetone actually, and squirted it into the flask, swirled it around, and tipped it down the sink. That's what we did with waste. We just tipped it all down the sink and washed it away. All these things you cannot do, and very good too, but life was simple in those days. But when I did that and tipped it in, nothing came out. So I looked at the flask, and it was absolutely full of beautiful crystals. The problem was a solvent one. Benzene, petrol, wouldn't crystallize it at all. But ethanol, which is what I'd actually picked up, ethanol, and it crystallizes. And all these compounds crystallize beautifully easily in ethanol. So now, with masses of crystals, I could do a combustion analysis and check that the formula was right. I was almost certain this is what I'd made, and so I carried out the reaction. And there we are. I treated it with sodium hydroxide to hydrolyze these two esters, the carboxylic acids, sodium salts off them, and the reaction took place overnight at room temperature. So that's much more like physiologically acceptable conditions. And it makes a centimetre. And now another thing that's different about those days from now, John said, oh, we must publish this, and we did. And there's our first paper. One reaction published. Now you have to have lots of them, show how general it is and so on, which we did go on to do. But there it is, one thing. And we draw attention to Tim Jones's there with the reference to his lecture, which I discovered. So that was nice. And in fact, what I then did was to go on to show how general this reaction was. As it says here, it says something about we're going to go on and look at this in general. And I did lots and lots of reactions. And everything went extremely well. And so I had another great chunk of my thesis for this. The calicanthy work didn't go in my thesis at all. But this was the beginning of it. It was about half my thesis. And then it was going so well, and John took it away from me and gave it to a new graduate student to make up for his PhD thesis. And I went on to something else, which I don't have time to talk about. Now, while all this was going on, we of course used to have lectures in these lecture rooms, the one next door usually, but we would have a lecture almost every week on Mondays at 5 o'clock from a visitor. We don't seem to do that now, but in those days, every Monday, 5 o'clock, there was a lecture. And one of the people who came during those 3 years I was a graduate student was a man called Colin Eborn. He later became very distinguished, FRS and all the rest, but at that stage he was a lecturer in Leicester. And he came and talked about some chemistry, which I'm just going to describe to you briefly, because it probably had a big influence on me without my quite realizing it. Okay, the reaction he was looking at was aromatic electrophilic substitution. And he found that if you have a silane group attached to a benzene ring, an electrophile, such as a proton, will attack the carbon the silicon's on, the most hindered carbon in the benzene ring. And that was, at that stage, rather puzzling. So he thought about that, and he was very, very tentative in that lecture. But he said it looks as though a silane group like that, next to a cation, except this is a p orbital here, p orbital on there, that silane group is better than a hydrogen atom at stabilizing that cation. Because if you were to attack any other position of the benzene, any other position here, you would have two hydrogen atoms there, and that is evidently not as good because it isn't formed as fast. So there's something special about attacking at the silicon carbon because it gives you a cation in which the silane group can stabilize the cation. But he made nothing much about that, and it was a terribly tentative idea in those days. But then he noticed something else about this reaction, and that is, it was irreversible. It didn't go backwards and forwards. The next thing to happen was that the silane group was taken out by the counter ion. And so that also suggested something, that the silane groups are better, now notice the terminology, a better electrofugal group than a proton, with the counter ion X is a hydrogen, basically. Again, he was terribly tentative about that. But if you look at those results, that's what it is telling us, those two facts. So, did I make anything of that then? No, I completely forgot everything. And one does. The first time you hear a lecture, you don't always take it away and say, wow, this is terrific. In fact, I didn't see any potential for that at that stage, but we're going to come back to it. Instead, I told you I did another whole series of reactions in a totally different area under John's supervision, and then on my own for a year. And then at the end of that, 4 years, I went to Harvard as a postdoc. And now I met the great Professor R.B. Woodward. Now, R.B. Woodward was the great organic chemist of the 20th century. Really no question about it. He was an astonishing man, and everybody who had anything to do with him was in utter awe of him. I know several chemists who really thought they were pretty damn good, but they all conceded, or at least all the good ones conceded, that Woodward was the top guy. So there I was at Harvard, the top man, pretty nervous, and knowing that I was going to have to work pretty hard. And the project I was going to work on was the one that he was looking at that time, which I knew what it was. He was working on the total synthesis of vitamin B12. Now, we're not going to look too much at that molecule. It's, as you can see, an extremely complicated molecule with a lot of difficulty in it. And that's what he was aiming to synthesize. He'd already synthesized chlorophyll, strychnine, lots of other molecules. And they were all beautiful and interesting syntheses with new chemistry all the way through. Here's B12. How to do this one. This was the Everest of organic synthesis. It still is in a way. And it's very complicated from the point of view of stereochemistry. To do this and synthesize this, all these stereo centers, especially these 6 down here, have all got to be controlled. Because if you have no control and you separate, you'll get very, very little of the product you want. So Woodward was at the very front of how to control stereochemistry in synthesis. And this is what I found myself with. So what was I doing? Well, they had already made this molecule. Bob Ramage and others had made this molecule here. And they controlled the stereochemistry of those 2 centers very well, because when you have a 5-5 ring junction like that, you can only really make it when it's cis. So the 2 methyl groups are on the same side. You might have a bit of difficulty seeing where this is going. In fact, if you look at that ring there, that 5-membered ring with the nitrogen, it becomes this one up here. Then are the 2 methyl groups coming through from this molecule to that. But it's a long way to go. My part, I was told to synthesize this acid chloride. And I was starting with camphor, which is enantiomeric pure. And so I had a molecule here with this carbon atom with this absolute configuration. It took me 13 steps and a 17% yield. That doesn't sound too good, but actually for 13 steps it's very good. It means that I had very good steps all the way down, but it was a lot of steps, of course. But I wasn't the only person on this synthesis. 2 other people were doing exactly the same. We were all working on the same project. And in the end, John Carnduff was the first person to make the acid, this acid down here, but he only had a few milligrams. Jean-Marie Lane came in later with the best synthesis, 19% instead of 17, but fewer steps, so it was easier. And I had the good fortune to be the first person to get here with a reasonable amount of, I had grams of it, so I wasn't in short supply of the acid chloride, and I had it in anti from PlusCalc, so I really had the compounds. So I was the lucky one to be able to join these 2 molecules together. So I did. So I joined this molecule to that one with an amide linkage from the amide and the acid chloride. And then I did the critical reaction, which was the bit that was most interesting. Potassium tertiary butoxide and tertiary butanol will form an enolate here, and that enolate will attack this carbon in a mital reaction, an intramolecular mital reaction. And it did that, and it gave 1 compound, that stentor and that one, perfectly controlled. So now you can see that here we are at the very front of stereo control, and I was doing it. So I come from a period when we didn't control stereochemistry core to be doing one of the most advanced examples of a stereo control reaction. And it worked beautifully like that. If you want to see roughly what's going on, I don't know whether you can see this, but you can see that the 2 5-membered rings are a sort of little envelope bent down like that, with the methyl groups down on the bottom. And this chain can only really come along on the top surface. It can't go past that methyl and come down. And so that carbon will attack this one. This group will be out over here somewhere. It's the big group. It's this, it's like a pentenon group. And so that will be over there. When the forms a bond from that carbon up to that one, that H will be up and that H will be down. And that worked so perfectly because it had been beautifully designed by Woodward to give exactly that result. And my experiments showed that it actually worked just as it should have done. And so we had this molecule. Or rather, now I have to admit, this is not exactly what I did. Because when I did this reaction, this molecule had not been resolved. And I had racemic tricyclic amine, that amine there. So when I did this reaction, I had 2 compounds like this. One from the compound with the 2 methyls down, and another one from the compound with 2 methyls up. So I actually had a mixture of these 2 compounds. Both of them have this center control from the camphor, where one of them has them all like that, and the other has them all like that. And they're diastereoisomers. But this was the big test to see if it would work. And so I knew I had to separate these and pull out each one. And so I did. And it was a very elaborate business. I had to have a big column, very careful chromatography. And eventually I discovered that I did get 2 peaks coming off the chromatogram. So I thought, I've got them. I've got the 2 isomers. One of them's the correct, one of them's no use at all. But what I need now is to get them pure. Now, once again, these really should crystallize. A polycyclic system like this, with these kind of functions, we should get crystals. So I had this smear of an oil, a few milligrams, in the bottom of a flask, and I tried scratching it, and nothing happened, and I tried changing solvents a little bit, nothing happened, no crystals. And then Woodward himself came up that afternoon. Now, he usually saw me at 11 o'clock at night. He left me to last for some reason. But on this occasion, because I was doing this critical reaction, which he was really interested to see, he came up in the afternoon. And I explained, he knew what I was doing, of course. And I explained that I got these 2 compounds separated. And he said, have you scratched? I said, yes, I gave it a scratch. He said, scratch it until it crystallizes. Well, what happened? Here it is in my notebook. This is my notebook from that time. And if you read this here, it says, down, it's on this level here down. E crystallized after 4 hours scratching. That's what I did. I started at about 2 o'clock, and I scratched in this flask on and on and on. And then at about 6 o'clock in the evening, I could feel that it felt different. It got a bit crunchy. So I said, wow. So I clamped it up on the stand, put in a cover of aluminium foil over the top so nothing would drop in it, and went off and had dinner. And came back to see a lovely line of crystals all the way down from where I'd been scratching at the top of the flask, right down to the bottom where the oil had been at the bottom. So I'd got a pure compound now. So I really had separated these 2. And so well, you can see it here. I recrystallized, 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 recrystallized. I went on recrystallizing until the melting point was constant and the rotation was constant, and I knew I had a perfectly pure compound. So now I had the compound pure. So I had made that. And of course, shortly after that, this was resolved, and we could do this reaction properly, the right way round, the wrong way round. We could do it all in the enantiomeric compounds as well, starting from plus camphor, using the opposite here, and pairing them all up. So I made all 4 possible compounds, including, of course, the one we want. And this molecule went on in the next 10 years that it took to complete the total synthesis of vitamin B12 using that molecule. And whenever I see the structure of vitamin B12, what I see is the 2 carbons there, which are my 2 carbons here, 2 stereocenters that I put in. And so I sort of grab that bond in my head and think, there's my bond. But it did take 10 more years and a lot of postdocs. And also collaboration with Albert Eschenmoser, who made a very big contribution to this. All right. I came back to Cambridge after that year at Harvard, and I did lots of different things. Nothing very much. Oh, no, there's another story to tell. Okay, these are a number of very distinguished organic chemists. Actually, not including me, but this is me over on the left-hand side. Taken in about 1980. And the person I want to draw attention to is W.S. Johnson over here. Johnson was a very substantial organic chemist who was interested in polyolefin cyclizations to make steroids. And one of the reactions he was looking at, and he came to Harvard in the year I was there and gave a lecture, just as Eborn came here and gave a lecture. And Johnson gave a lecture which he was trying to do the simplest possible ring-forming reaction in which a double bond and a carbocation might combine to form a ring. And he was studying this with very great care. So he took this acetal, treated it with acid so that it gave this intermediate, and wanted to know if it would cyclize with that carbon attacking that one to give this bond here and a new cation. And he found that it did that reaction extremely well, very cleanly, but it gave a lot of products. They all have that bond in. But there are 2 cations capturing a nucleophile and 3 alkenes, because that cation can lose a proton from here to give this compound, can lose it from the beta group to give this one, and it can lose it from this carbon to give this one. And on top of that, actually, this is unstable in acid, and so it was going on to give a diene. So it was a horrendous mess from the point of view of synthesis. But it was not from Johnson's point of view, because it was very cleanly, every single product had that bond in it. And that was what he was trying to learn about. And he then went on to look at more and more complicated examples. But this revealed to me in 1964, that there was a problem with carbocations. Again, it was in my mind, but I did not pay very much further attention to it. I came back to Cambridge. I did a lot of different things. I love chemical reactions, and I love thinking about it. And so we did lots and lots of different chemical reactions. And they were nice, a lot of publications. And in 72, 71, 72, I went on sabbatical leave, and I went to Montreal, and there I made a point of reading that book. Now that's my tattered copy of it, or rather the tattered cover of the copy, because it was the Bible for me and my research group from then on. That book contains a very long chapter by Colin Eborn on organosilicon chemistry, the silicon-carbon bond, how to make it and what it does. And in that book, and that review, he made explicitly the 2 statements that I showed you earlier. The silyl group stabilizes a neighboring cation better than a hydrogen carbon. It's called hyperconjugation, but it does, it's quite effective. And secondly, if you get such a structure, it'll be the silyl group that will come out rather than the proton getting lost. And now I thought, this is how we're going to sort out Johnson's reactions. Because if we know this, we can do control of what that carbocation. We've just got to build the silicon in by some route like these arrows in tank. And if we can do that, we'll control the outcome. And why was it I who first thought of this and first put this all together? The reason is that I was alert to the idea of a different electrofugal group. You remember I was looking at decarboxylated eliminations here. I was familiar with the idea that there is such a thing as an electrofugal group. Most chemists at that time would not have been able to use that language. And I had it in my perception straight away. And so I was very alert to the idea that you could use a different electrofugal group. All right, so I came back to Cambridge and we tried. And you can see what to do. First person was this graduate student, Andrew Pierce. He was able to take this chloride and convert it to the silyl group. You just have to treat it with sodium with Dimas chloride and you'll get the allyl silane. And of course, we tried the reaction. And it was perfect. The only product was this one. I know the others were good and we didn't work it up to be great here, but there were none of the other alkenes, only this one. And so that's the way to do it. Put the silyl group where you want the double bond to form, and you will get only that alkene. So that's the idea, controlling the outcome of carbocation reactions. Now the other molecules we need to be able to put a silyl group here, and we need to be able to put it on here without that one. And that wasn't obvious in those days. There were no synthetic methods that looked as though they would work. And so a large part of our work for the next 4 or 5 years was working out how to build compounds with silyl groups in all sorts of different places, so that we could use the idea of taking the silyl group out. And we did. We worked out methods by which we could make these 2 silanes. We made this compound, which has the silicon in that position. And we made both isomers of this, the Z and the E isomer of the vinyl silane, and we treated those with acid, and they were perfect. This one gave only this alkene, and this one gave only that alkene. The yield here is low because this is unstable. And if you leave it, it was slow with this isomer, and because it was slow, the product sat in the acidic medium and went on to dehydrate and gave the diene. but that was the only reason it's a low yield. In none of these cases was any of the other alkenes present. And because we used standard chloride instead of protic acid in methanol, we didn't suffer nucleophilic attack either. And so, there we are. We demonstrated that the way you control a carbocation outcome is to build a silyl group into the place you want the double bond to form. And that was a major contribution which we did. Right, back to that photograph of people, and this time a different person. Incidentally, this over here is Jean Mathieu, who introduced that language. I bet you'll find that if you ask an organic chemist who introduced that language of electrofugal and neutrophil, they won't know. But it was in fact Jean Mathieu over here on the right. All right, the other person is this guy over here, Barry Trost. He's an old friend. I've known him for a very long time. And at a scientific meeting somewhere, he came to me and said, what do you do if the silyl group gets lost from the functionality? And I knew exactly what he meant. I said, well, we're working on it, and it's happened to us. And this was the context in which it happened to us. First, we were looking at carbocation reaction, but this time the carbocation is not next to the silicon. And we reasoned that if you have a carbocation there, this group will migrate to it to produce a cation next to the silicon, because that will be down here. And then the silicon will drop out and put the double bond there. And that's what happened with all these various groups over here. Lots of people worked on variations of this sequence of reactions. But one example of it gave us a funny reaction. That was done by Georges Vittel here. When we opened this epoxide to create a cation, we were hoping it would do a rearrangement to give this hydride shift to there, silicon dropping out. But that's not what happened. What happened instead was that the epoxide, the oxygen, pushed this hydrogen out. In other words, the lone pair is even better at stabilizing a cation than the silyl group is. Not surprising. And so what we got was a molecule like this with an aldehyde here, but the trimethyl silyl group now is way out in the middle of nowhere, right? It's at the edge. There's no functionality. You will not be able to do anything with it. In fact, the only reaction it would be capable of would be to react with a very powerful electrophile. And even then, it would be the methyl groups that would be attacked, not the methylene. And so you're stuck. So that was what Barry Trost meant by what do you do when the silyl group is stuck out in the middle of it. But even more important, we discovered a reaction. And here it is, done by David Waterson. He was adding the silyl cuprate to this unsaturated ester cinnamate. The silyl group goes in the conjugate position to give an enolate. And when we worked up with methyl iodide, we got methylation. And to my complete surprise, he came to me saying, there's something wrong, there's only one product, there should be two. We should get both stereochemistries, the methyl group on the top and the methyl group on the bottom. Why have we got only the one? 97 to 3. And this is an open chain stereocontrol. And in open chains with no benefit of rings or cyclic transition structures, 97 to 3 is an astonishingly good level of control, stereo control. It's probably the best there is. And we got it by chance. Well, I looked at this and thought, well, that's very extraordinary. What's more, it's a very pregnant idea because this is going to give us a lot of possibilities for organic synthesis. And it was easy to see what the stereochemistry must be. Because if you look at that enolate there, only the H will want to sit inside here. These two groups are too big to go in here, bumping up against that oxygen, or the other one, depending on the geometry. And therefore, the difference between the top and bottom surfaces is a very big group, with great big groups sticking out in all directions. And the phenol group. Normally you think of phenol as big, but it's not doing much to shield the lower surface, whereas this group, with its bonds, is shielding that top surface. And so the electrophile can really only attack on the bottom surface. And that's why we got this level of stereo control. And it was in this sense, of course. And now you can see the silyl group is stuck away from the functionality. How can we do anything with it? Well, I told you right at the very beginning what we can do with it. This is where the silyl-to-hydroxy conversion comes in. And Phil Sanderson over here developed this recipe. Potassium bromide, you don't need bromine, because potassium bromide in pure acetic acid gives you bromine, and so you get bromine doing the electrophilic substitution of this phenyl group, and then the peracetic acid does all the rest, and you work up, and you get phenylethyl silyl converted into hydroxy. And stereochemically important, that kind of reaction always goes with retention of configuration. So the stereochemistry we've got could be continued with in the next stages. So that's why we discovered this reaction. We were working with silicon compounds, came across stereocontrol, the very thing I said we couldn't do at the beginning of my career. Now we're doing it in the very best way. But I didn't discover this reaction. I actually knew it was going to work. It has been known from before I even started research, from 1956, from a man called Elwin Davis. Now, Elwin Davis was a radical chemist, and not a synthetic like that. And he was trying to make a trimethyl silyl ester of a peracid. So he treated trimethyl silyl chloride with perbenzate. And he found that it didn't, it rearranged. One of the methyl groups came off, the silicon went onto the oxygen, and what he made was methanol. The world's worst, most appalling synthesis of methanol, certainly one of the most expensive. You wouldn't dream of making that. But that was as far as Bunsen and Davis went. They had made the compound, they'd found the reaction, but they were not synthetic chemists, and they didn't see that it had any potential at all. Fortunately, I was lucky and came across this paper and thought, that's how we'll be able to do our reaction. We'll be able to oxidize it with peracid. And that was before Tamao had done any of his work. And so I knew when we set off on that route of chemistry that we would be able to do that reaction and we would get the silyl-to-hydroxy conversion. That's my talk. You can see what I've done. I started with the idea, started with where we were going, and we covered the idea of what do you do without NMR. The answer is we didn't need it, really, for those early reactions. And then we finish up with really complicated chemistry, because that 97:3 ratio, how do you measure it? NMR. Thank you.
Thank you, Professor Fleming, for the wonderful talk. Does anybody have any questions for Professor Fleming?
Yeah.
Yes.
So apart from health and safety, what have been some of the biggest changes in synthetic chemistry throughout your career?
Well, just for a start, there are some women in the audience. When I was a graduate student, there was one woman in the department who was a graduate student at the same time as me. She was actually wonderful and a very good chemist, and she became an FRS and all the rest. She was an undergraduate contemporary. My undergraduate career, there were 3 women in the whole class, 95 men. So that's the biggest single and most obvious change. We have women. Everything else, well, you can tell from my lecture what happened. A huge change in what we can do in chemistry because of NMR. Because we can look at structures that we couldn't dream of analyzing before. And now we can, very easily.
Anybody else?
Yeah.
Thanks for the talk. So the terms electrophile, nucleophile, and I had no idea where they come from, but you mentioned.
Oh,
a little bit about
nucleophile and
the history.
electrophile are long-standing words.
Right.
What I'm talking about was nucleofugal.
Oh, okay,
Electrofugal.
right. Oh, okay.
An electrophile is usually a cation that can attack an electron rich.
Right. Okay. No, I misunderstood. So it's electrofugal and.
It's
yes,
electrofugal.
okay.
Fugal means leaving,
Yes.
going.
Okay. But we don't see these terms much these
No, we
days.
don't, but you do sometimes when you need it, as I needed it for here.
Right.
I needed to establish the 2 kinds of leaving, with and without the electrons. And so that's the way you describe that problem.
Thanks.
Any other questions? Or
Yes.
This might be a bit silly, but what's the actual benefit of like synthesizing that vitamin K molecule? Like,
The
what
benefit of
does it-
synthesizing vitamin B12?
Yeah, B12, sorry. Sorry.
Well, they did make actual, totally synthetic vitamin B12, and it was an achievement. And in order to do it, an enormous amount of inventive chemistry had to be produced. And so, yes, it was worth it. It was a towering achievement, and everybody recognised it. As it happens, in the course of that work, some reactions were discovered that were totally revolutionising of our understanding of organic chemistry. They're called pericyclic reactions. And the rules of pericyclic chemistry came because during the vitamin B12 synthesis, Woodward saw something happen stereochemically that he did not expect. It was the exact opposite of what he expected. And when he thought about it longer, he realized that it's got something to do with the molecular orbitals, and a huge area of organic chemistry was unearthed called pericyclic chemistry, and he developed the rules for which reactions can and can't take place in those. But that's a very big story, and if you do chemistry, you'll come across it in the second or third year. But yeah, in the second year, isn't it? Second year chemistry.
More third year.
Yeah, yeah. It comes in second year organic courses now. It's a very important set of ideas, and it actually came out of the vitamin B12 synthesis. So this particular synthesis was very, very pregnant. Yeah.
So is vitamin B12 still considered the most complex molecule?
Well, no, it isn't now. There are some very, very complex natural products got out of the slime of sea creatures. And they're just huge. I mean, they got absolutely astonishingly large.
And what do you think, in your opinion, is the most complex
Oh,
ever
I don't know.
synthesized to date?
I've forgotten the name of it. But people working on the synthesis, oh yeah. Yeah. A man called Kishi was the architect of that. Kishi was one of the people on the B12 synthesis. Oh, what's happened? Oh, I see. It's still showing up.
Any other questions?
Yes.
Yeah, thank you for the fascinating talk and story. So I'll ask a specific question. You showed us your first manuscript. That
Yes.
was one reaction.
Yes.
Wonderful. And always I hear from colleagues that it used to take very long to publish in the earlier years. But I noticed from submission to publication it was only 2 months.
Yeah.
If I haven't read it incorrectly. Was that typical from your experience, or was this?
Yes, I think for that journal, which was not a big journal for organic synthesis, but it allowed people to put. It wasn't usual in those days to have preliminary communication. If you did have a preliminary, it was something very small like this, one reaction.
But it could get out to the community quick enough.
Yes, I mean, I was lucky, I suppose. It got published straight away.
That's right.
Yes, that's another difference from the day.
Yeah.
Yeah.
Any more questions anybody has for Professor Fleming?
Yeah.
Yes.
Thank you so much for the talk. I was just curious, as an open question, whether there's any other progress in organosilicon chemistry in terms of further ways of controlling reactions, if you do know of any.
Well, I'm sure there is, but for the last 20 years I have not been active in the field, so I really don't know the advances in that area. I think probably that period from 1975 to 1990 was the big period of organosilicon chemistry, and lots of people piled into the work, and I was very lucky. Nobody else did what I was doing, so I didn't have anybody do something ahead of me. They did things that I wanted to do, but hadn't got around to, especially Scott Denmark. He did something that I wish I'd done what he did. But no, lots of people, a lot of people worked in it, and there are big fat textbooks of organosilicon chemistry with the reactions that might be useful in synthesis. But my part was to be, I'm a synthetic organic chemist, what can we use silicon for?
Any last questions? Well, if not, could we please put our hands together again to thank Professor Fleming?